Good morning, everyone, and welcome to today's presentation. I am Dr. S.K. Singh, and I am pleased to have the opportunity to discuss with you the fascinating topic of calculations of specific optical rotation. Today, we will explore what optical rotation is, how it can be measured, and the methods used for its calculation. I look forward to sharing insights and engaging with you throughout this session. Let's get started. Let's start by understanding what specific optical rotation, or alpha, actually means. It is defined as the optical rotation produced by a solution that contains exactly 1 gram of the substance per milliliter, measured in a tube that is 1 decimeter long, under specific temperature and wavelength conditions. This helps us standardize how we measure optical activity across different substances and conditions. We often see it represented as alpha with a subscript indicating the temperature, T, and the wavelength, lambda, at which the measurement is taken. Now, moving on to the concept of optical rotation itself. This refers to the phenomenon where plane polarized light is rotated when it passes through an optically active substance. This property is really important because it allows us to identify and analyze chiral compounds. To measure this rotation, we use a device called a polarimeter. It's a crucial tool in our field, especially because it helps in identifying substances, determining their concentration, and assessing purity. This technique isn't just limited to one industry. It's widely applied in pharmaceuticals, chemicals, sugar production, and even the food industry. Each of these fields relies on optical rotation to ensure quality and consistency. So, to sum up, the specific optical rotation gives us a standardized way to quantify how much a substance can rotate plane polarized light, which in turn helps us understand its chiral properties and purity. This measurement is fundamental in many industrial and research applications. Optically active substances have the interesting ability to rotate plane polarized light as it passes through them. This rotation can actually go in 2 different directions. When the rotation is clockwise, we call it dextrorotatory or simply positive, indicated by a plus sign. Conversely, if the rotation is counterclockwise, it's known as levorotatory or negative, marked with a minus sign. Now, the degree to which light is rotated isn't fixed. It actually depends on several factors. These include the type of substance we're dealing with, its concentration in the solution, and the length of the path the light travels through that substance. Temperature and the wavelength of the light are also important because they influence how much rotation occurs. This brings us to the principle of specific optical rotation. Essentially, it's a standard way to quantify this rotation, considering the substance's characteristics, the concentration, and the path length. It helps us understand and compare the optical activity of different substances systematically. Understanding these concepts is key to grasping how optically active compounds behave, which is fundamental in fields like stereochemistry and analytical chemistry. Let's take a closer look at the main components of a polarimeter. First, we have the light source, which can be a sodium lamp or an LED. This provides the initial polarized light needed for the measurement. Next, there's the polarizer, which ensures the light is properly polarized before it passes through the sample. The sample tube holds the substance we're testing, allowing the polarized light to interact with it. After that, we have the analyzer, which helps us determine how much the plane of polarization has rotated due to the sample. The detector or eyepiece then captures the light that emerges from the analyzer. Finally, the digital display or data processing unit interprets the data, giving us the optical rotation measurement. These components work together seamlessly, allowing us to measure the specific optical rotation accurately, which is essential in characterizing chiral compounds. Understanding these parts helps us grasp how the polarimeter functions as a precise analytical instrument. Let's go over some important precautions to ensure accurate polarimeter readings. First, always make sure the polarimeter tube is clean and dry before use. Any dirt or moisture can affect the measurement, so take a moment to check it thoroughly. Next, be careful to avoid air bubbles in your sample solution, as they can distort the reading. If bubbles appear, gently tap the tube or prepare a fresh sample. It's also crucial to use the specified solvent as per the method you're following. Different solutions can impact the optical rotation, so sticking to the recommended solvent ensures consistency. Maintaining a constant temperature is another key factor. Temperature fluctuations can change the optical properties, so keep your environment stable throughout the measurement. Additionally, use the correct tube length specified for your experiment. Using the wrong length can lead to inaccurate calculations. Finally, always record the rotation only after the reading has stabilized. Don't rush. Wait until the needle or digital readout shows a steady value before noting it down. These precautions help ensure that your measurements are precise and reliable, which is essential for the overall accuracy of your analysis. Now, let's take a closer look at the formula for specific optical rotation. It's written as alpha equals alpha divided by the product of L and C here. Alpha represents the specific optical rotation, which is a standardized measure. The alpha is the observed optical rotation, the degree to which the plane of polarized light is rotated by our sample. The variable L is the length of the polarimeter tube, measured in decimeters, and C is the concentration of our solution, expressed in grams per milliliter. To make this clearer, let's consider an example. Suppose our observed rotation alpha is plus 25 degrees. If our tube length L is 1 decimeter, and our concentration, C, is 0.05 grams per milliliter, then plugging these into the formula gives us alpha equals 2.5 divided by 1 times 0.05, which simplifies to plus 50 degrees. This calculation is key because it allows us to compare the optical activity of different substances under standardized conditions, regardless of the sample size or concentration. Remember, understanding how to compute the specific optical rotation helps us analyze and compare chiral compounds more accurately. It's a fundamental concept that ties into the overall theme of measuring and interpreting optical activity in stereochemistry. Optical rotation, or alpha, is a fascinating property exhibited by certain substances. It refers to their ability to rotate the plane of polarization of polarized light passing through them. When a substance has this ability, we say it is optically active. This property is quite characteristic of some crystals, as well as many pharmaceutical liquids or solutions of solids. Understanding optical rotation helps us identify and analyze these substances. Now, a specific concept related to this is the specific optical rotation. For example, when we measure how much a substance rotates the plane of polarized light at a particular temperature and wavelength, we get its specific optical rotation. This measurement is crucial because it allows us to compare different substances and their optical activities in a standardized way. In summary, optical rotation is a key property that reveals the chiral nature of certain materials, which is especially important in fields like chemistry and pharmaceuticals. It's a powerful tool for understanding the structure and purity of these substances, connecting directly to our broader theme of analyzing and characterizing materials. Now, let's look at some practical applications of the techniques we've discussed. First, the identification of optically active substances is crucial in many fields, especially in pharmaceuticals and natural products. Knowing whether a compound is optically active helps us understand its structure and potential biological activity. Next, purity testing of chiral compounds is essential to ensure the safety and efficacy of drugs. Even small impurities or the presence of the wrong enantiomer can have significant effects, so accurate purity assessment is vital. Sugar analysis is another key application, particularly in the food industry and biochemistry. Determining the optical activity of sugars helps us understand their purity and structural properties, which can influence flavor, stability, and nutritional value. Finally, optical activity plays a significant role in quality control of pharmaceuticals. It helps verify that the active ingredients are the correct stereoisomers, maintaining consistency and ensuring the desired therapeutic effects. Overall, these applications highlight how understanding and measuring optical activity is integral to ensuring quality, safety, and effectiveness across various industries. For further support, please don't hesitate to contact us. We're here to help with any questions or additional information you might need. Remember, our goal is to ensure you feel confident and well-informed about everything we've covered today. Thank you so much for your time and attention. We truly appreciate your engagement and look forward to assisting you further.